Sulfur dioxide at a temperature of 204 degrees Celsius occupies a volume of 0.3 meter cube. A. If the volume is increased to 0.9 meter cube while the pressure is maintained constant, assume ideal gas behavior, what is the final temperature in Kelvin and in Celsius? Letter B. If the initial volume is maintained constant and the pressure is tripled, what is the final temperature in Kelvin and in Celsius? Sulfur dioxide at a temperature of, let's say, we just put number 5 here. Number 5. Sulfur dioxide at a temperature of 204 degrees Celsius occupies a volume of 0.3 meter cube. So at temperature 1 equals 204 degrees Celsius, and then the volume 1 is 0.3 meter cube. At condition A, if the volume is increased to 0.9 meter cube, so this means our volume 2 now becomes 0.9 meter cube, while the pressure is maintained constant, ideal gas behavior, that means P is equivalent to C. C means constant. What is the final temperature in Kelvin and in Celsius? So we are asking for our temperature 2. That will be in Kelvin and in Celsius. And our condition B, if the initial volume is maintained constant, that means V equals C, and the pressure tripled, and P2 is equivalent to 3P. What is the temperature in? Now we are solving our temperature 2 in also the same Kelvin and in Celsius. So these are our given values and our clues in order to solve for this problem. So let's start with condition A. Condition A, we are going to solve for temperature with the things that are known are volume 2 and the constant pressure equals C. So just like any other ideal gas problems, the first thing that you would write in order for you to work upon is the ideal gas formula, and you need to determine which amongst these ideal gas formula, these variables are constant. So it's already indicated or stated that pressure is constant, so therefore this will be crashed out. And then volume changes because volume 1 and volume 2 they are given, and our mass is not specified, therefore mass would also be considered as constant. And then since this is this is the same gas, we are dealing with only one type of gas, which is sulfur dioxide, therefore our gas constant is also constant. So the only things that we are going to work with are the volume and temperature. So transposing them at the left, the constants to the right side, and transposing the non-constants at the left side, the formula now becomes V over T is equivalent to mR over P. And since these things at the right are constants, so therefore we can transform our formula into volume 1 temperature 1 equals volume 2 temperature 2, just like that. Now since we already have these values, they are already given, and we are going to solve for our main goal is to solve for our temperature 2. We are going to transform our formula. So temperature 2, solving for temperature 2, this will become temperature 2 is equivalent to volume 2 temperature 1 divided by volume 1, and substituting the values, our volume 2 is already given 0.9 meter cube, and our temperature 1 is already given 204 degrees Celsius, so we need to convert that one into Kelvin. So 204 plus 273, and the unit will be Kelvin. And then our volume 1 is 0.3 meter cube. Alright, so that's for temperature 2, and now temperature 2 is 0.9 times 204 plus 273 divided by 0.3. So temperature 2 is 1431 degree Kelvin, or converting this one back to Celsius because we need to solve it both in Kelvin and in Celsius. So we just need to deduct it by 273. So answer minus 273. That means the temperature 2 in Celsius is 1158 degrees Celsius. Alright, that's for condition A. Now let's jump to condition B. At condition B, at condition A, the constant is pressure. Now in condition B, the volume is constant. So same thing, we need to write our ideal gas equation. Now we are going to determine which amongst these variables are constant. So it's already indicated that volume is constant, so this needs to be cashed out. And since mass is not specified, therefore mass is also constant, and the ideal gas constant is constant also. So since we are already dealing, only dealing with sulfur dioxide, that means our formula now will transform into pressure 1 over temperature 1, since we are going to transpose, we are going to put temperature 1 at the left side, so we need to divide both sides by temperature 1, temperature. So our formula now becomes pressure 2 over temperature 2 equals pressure 1 over temperature 1. Now the next step that we will do is apply the things that are given. So it says here that it says here that pressure is tripled. So that means pressure 1, let's say pressure 1 equals P, and then pressure 2 equals 3P, because at B it is stated that the pressure is tripled. So this will be that means our initial pressure is stated as P, and then our pressure 2 is tripled on our initial pressure. That will become 3P. So solving for our temperature 2, this will now become pressure 2 temperature 1 all over pressure 1 is equivalent to, our pressure 2 is 3P, and then our temperature 1 is given, which is 204 degrees Celsius. So 204, converting this one to degree Kelvin, so we need to add 273, and then dividing this one by our pressure 1, which is P, so cancel P. We can now solve for our temperature in Kelvin. So temperature is equivalent to 3 times 204 plus 273, 1431 degree Kelvin, and temperature 2 in degrees Celsius is, you need to just deduct it by 273, 1158 degrees Celsius. So that means at constant pressure and at constant pressure on state 1 and at constant volume at state 2, temperature and all the temperatures would be equivalent, just like that. As you can see, the temperature here in Kelvin is the same, and the temperature here in Celsius, they are the same. So that's for problem number 5. A steel company plans on using 17 meter cube of oxygen gas in processing 1 metric ton of steel. If this volume is measured at 101.325 kilopascals absolute and 21 degrees Celsius, what mass of oxygen 2 is needed for 20,000 metric ton or a month of furnace? So our given volume 1 is equivalent to 17 meter cube, and then the material used is oxygen 2, and the volume is measured at the pressure of 101.325 kilopascal absolute and a temperature of 21 degrees Celsius. Now the question is, what mass of oxygen is needed for a 20,000 metric ton or month of furnace? So we are going to be asking for our mass 2, and our mass 1 is also unknown. So these are for 1 metric ton of oxygen 2. So just like any other ideal gas problems, we need to write down our ideal gas equation. So we have our at state 1, we have our pressure, volume. We can we can solve for our R, and our temperature is also given, so we can solve for our mass 1. So solving for mass 1, this will now become pressure 1, volume 1 all over our temperature 1. Now, since pressure 1 is given, volume 1 is given, temperature 1 is given, the only thing that we need to look for is our gas constant. So the formula for gas constant, the value for gas constant is R is equivalent to, since this is in metric system, 8.314 kilojoules per kilogram degree Kelvin, and dividing the constant 8.314 by the molecular weight. And molecular weight for oxygen, we know that oxygen is 16. The molecular weight of one atom of oxygen is 16. Therefore, since this is diatomic, therefore the molecular weight of oxygen is 16 times 2, which is equivalent to 32. So R now becomes, for oxygen, 8.314 kilojoules per kilogram degree Kelvin. Dividing 8.314 by 32, our R, or gas constant, becomes 8.314 divided by 32, 0.2598. So 0.2598 kilojoules per kilogram degree Kelvin. Alright, so that's for our gas constant. Now, since we already have our gas constant, we can solve for our mass 1. So mass 1 equals pressure 1, which is 101.325 kilopascal absolute. I'm just gonna write this one in its simple form. So this will be kilonewton per meter squared. And then the volume 1 is also given, 17 meter cube. And then dividing this one by our gas constant, 0.2598. So 0.2598 kilojoules per kilogram degree Kelvin, and then multiplying this one by our temperature. Temperature 1 is given as 21 degrees Celsius, so we need to convert 21 degrees Celsius to Kelvin by adding 21 plus 273, and the unit will now become Kelvin. So cancelling the units, degree Kelvin is cancelled. We need to write this kilojoules into its simple form. So I'm just gonna put it here at the left side, the right side, kilonewton meter. It's like that. So I cancel my kilonewtons, and I can cancel my meter squared here. I'm left with another one unit of meter. Since there's also a meter here at the denominator, so I can cancel this one also. So I am left with a unit of mass, which is in kilograms. So mass 1 equals, simplifying it by doing the division, so 101.325 times 17 divided by 0.2598 times 21 plus 273. That will be in open close parenthesis, just like this, and the answer is 22.5517 kilograms. So 22.5517 kilograms, just like that. So I already have a value for my mass 1, and now this is for 1 metric ton. So that means for 1 metric ton, the amount of mass, the mass of oxygen that we are going to consume in processing steel is 22.5517 kilograms. So how much do we need to spend, or how much of, when it comes to mass, are we going to consume in 20 metric tons of steel? So that means we are just going to simply apply ratio and proportion. That means at mass 1 we can get 1 metric ton, and at mass 2 we can get 20,000 metric ton. So by applying ratio and proportion, we're just gonna cross multiply this one, solving for our mass 2. Mass 2 is equivalent to mass 1 times 20,000 metric ton all over 1 metric ton. It's like that. So mass 2 equals, so metric ton, the unit of metric ton gets cancelled, so what we're left with 20,000 and our 22.5517. So 22.5517 kilograms multiplied by 20,000 all over 1. So mass 2 is equivalent to 22.5517 times 20,000 over 1. So that means the amount of mass that we are going to consume of oxygen is for in processing 20,000 metric ton of steel is 451,034 kilograms. Alright, so that's for problem number 6. It is planned to lift and move logs from almost inaccessible forest areas by means of balloons. Helium at atmospheric pressure 101.325 kilopascals absolute and a temperature of 21.1 degrees Celsius is to be used in the balloons. What minimum balloon diameter, assume that the shape is spherical, will be required for a gross lifting weight of 20 tons? Helium at atmospheric pressure, so pressure is 101.325 kilopascals absolute and the temperature of 21.1 degrees Celsius is to be used in the balloons. So the material used in the balloons, the gas is going to be used in the balloons is helium. What minimum balloon diameter, assume spherical, will be required for a gross lifting weight of 20 tons? So that means the balloon diameter being asked here is the total amount of balloons being put together in order to lift a certain number of logs with a weight of 20,000 kilograms. So I'm just gonna draw here one balloon. This will represent the numbers, number of balloons that are being put together in order to move logs. And then I am going to illustrate it just like this, and I'm gonna put some string or whatever rope is going to be used and some logs here to represent the material being lifted. It's like that. And as you can see, since it is under the if you're going to make a balloon float and put something in it, it is actually being submerged in fluid, and the type of fluid being submerged in is actually air. So since we are submerging, let's say there is air here at the surrounding, just like that. I'm gonna represent the air, the amount of air, just like this. And as you can see, if a material is being submerged in fluid, it is now being under the subject of buoyancy. In the law of buoyancy, or in the concept of buoyancy, the force of the fluid being submerged in, so I'm gonna put here air, since that is the gas where the logs and the balloon is being submerged in. The force of air, if it is greater than the force of the material, so that will be force of helium plus force of our logs, then therefore the material will float. But if the force of air is less than of the force of the helium plus the force of logs, then therefore the material will sink. Now, so that is the general concept. Now the question is, how do we make our force of air greater than the force of our helium plus our force of a log? So how do we make or create our air to be greater than, or to be of stronger compared to the forces, because these are downward forces, because this is we're talking about weight of the material of the lugs and also weight of the helium. So that would be downward force, and in order to counter a downward force, the force of air should be upward. So that is the concept of buoyancy. Now, how do we make our force of air greater than of the force of these two materials? So the answer there would be the amount of air the amount of air displaced should be great. So in order to make the amount of air displaced, we need to make the diameter or the volume of the diameter of our balloon to be also great. So, or huge. So that means our balloon needs to be a certain a few meters when it comes to its diameter. It needs to be great in diameter in order for it to lift a certain number of logs, and in order for the amount of air displaced to be great, and in order for it to float. So since force is defined as mass times gravity, and gravity is constant, especially if we are in standard condition, therefore we can cancel out gravity on all three of them. That means the force of the air, or we are depending on either the material will float or sink. It is now totally dependent on the mass of air, the mass of the helium, and the mass of lugs. So that means if you're gonna put it in simple words, mass of air should now be greater than mass of helium plus mass of lugs in order for our materials to float. So in order to make our mass of air greater than mass of helium and mass of lugs, the balloon should displace a certain huge amount of air in the sky in order for it to float. So in order to do so, our diameter should be huge, or our balloon should be huge in order for it to displace a certain required amount of air. So now, in solving this type of problem, we need to solve for the mass of air, mass of helium, and we already have the mass of lugs, and then equate it in order for us to have a volume of the volume of our balloon. And since volume is defined as 4/3 pi r cube, we can solve for our radius, and radius, multiply it by 2, we can solve for our diameter. And the first step is we need to solve for the mass of our I'm gonna solve first for the mass of my helium. So for helium, the general equation should be the same. PV equals MRT, and mass here would be the mass of my helium. So in order to solve for the mass of helium, mass is equivalent to pressure volume all over the gas constant times the temperature. Now, solving for this, we already have a given, pressure and temperature is given, and the volume is not given because this is what we are going to solve for. And by the way, the volume of the spherical balloon is also equal to the volume being displaced the amount of air, the volume of air being displaced, because whatever volume of this balloon is, that is also the volume being displaced with regards to the amount of air. So it is totally dependent. That means volume is totally dependent on the diameter of our balloon, and the volume of air also dependent on the volume of our balloon. So that's why, just like at what I mentioned before, in order to make our mass of air great, we should make the diameter, the volume of our balloon to be also great, so that in displacing the amount of air, it was also if submerging this one into a certain fluid, which is air, that means it can displace a huge amount of air to force these two materials to float. So that is the concept of buoyancy. And now, solving for the mass of our helium, we already have a pressure of 101.325 kilonewtons per meter squared, and our volume is unknown, so I'm just gonna put it as V. And then the gas constant for helium in metric system is 8.314 kilojoules per kilogram degree Kelvin, and it will be divided on the molecular weight of our helium, which is approximately 4, and the temperature of our of the surroundings is 21.1 degrees Celsius. So we need to convert this one in the absolute form. So 21.1 plus 273, that will be in degrees Kelvin. I'm gonna cancel out my units. Kilojoules can be written as kilonewton meter. I'm just gonna put that here at the side. So kilonewton will be cancelled and meter will go on top. So that means, will go on the denominator and kilogram will flip to the top. That means our mass of helium will now become 101.325 divided by that's 101.325 divided by 8.314 all over 4 times times 21.1 plus 273 equals, that means the mass of air is 0.1658 kilograms per meter cube volume, because volume is unknown. That is what we are going to solve for. It's like that. And then our mass of air being displaced is actually directly proportional to the volume of our spherical balloons. So mass of air is also the same as pressure volume all over RT, where the pressure is constant because the pressure of the surroundings is constant, 101.325. The temperature is also constant. The volume is constant since it is directly dependent on the volume of the balloon. So whatever volume of the balloon is, that's the volume of air being displaced, and and it is directly proportional to the mass of air also being displaced. And the mass of air being displaced is not equal to the mass of helium being displaced because their gas constant is not the same. If the gas constant of helium and air are the same, that means their mass being displaced, or their mass of helium and mass of air being displaced would be equal. But since they are of different gas constants, that is why it is not equal. But just like what I've said, mass of air will be directly proportional to the volume of our balloon. Now, solving for our mass of air, pressure is 101.325 kilonewtons per meter squared. That will be 4 kilopascals, and times the volume, because that is what we are going to solve for. And our gas constant is 8.314 kilonewton meter. I'm just gonna write this as kilojoules as kilonewton meter all over kilojoules per kilogram degree Kelvin, and I'll be dividing 8.314 by the molecular weight of air, which is approximately 28.97, and multiplying it by our temperature. Absolute temperature is 21.1 plus 273 degrees Kelvin. So cancel units, cancel kilonewton, and kilogram will flip to the top, and meter squared will be multiplied to meter. Now it will now become 101.325 divided by 8.314 over 28.97 times 21.1 plus 273. Now the mass of air being displaced is 1.2005 kilogram per meter cube volume. As you can see, mass of air being displaced is greater than the mass of helium, and the question is why? It is because the gas constant of air is lower compared to the gas constant of helium. As you can see, the gas constant of air, 8.314 divided by 28.97, is 0.28 or 0.29. On the other hand, the gas constant of helium is 2. That means air is significantly heavier compared to our helium, because their gas constants are actually the gas constant of helium is greater than the gas constant of air, and we all know that the gas constant is indirectly proportional to the mass of the gas. So the greater the gas constant, the lesser the weight, or the lesser the mass of the gas is, the greater the gas constant is, the lower the gas constant, the greater the mass is. So that's why the since air has lower gas constant, the value of the gas constant of air is lower than of helium. That's why air is much more heavier compared to helium. Given the fact that they have the same temperature, they have the same pressure, they are sharing the same volume. So that's why air will always be heavier compared to helium. So that's why if you use helium as a material as the gas to fill your balloon, it will always float. And now now we already have our equation 1. This one, mass air is equivalent to mass helium plus mass logs. So I'm just gonna write it again. Mass air equals mass helium plus mass logs, just like that. And substituting the values that we have arrived, 1.2005 kilograms per meter cube volume is equivalent to 0.1658 kilograms per meter cube volume plus 20,000 kilograms. That's for 20 metric tons. And now we cancel out kilograms as a unit, and then we transpose common units. So 0.1658 will be transposed to the other side. So 20,000 here is equivalent to 1.2005 volume per meter cube minus 0.1658 volume per meter cube. And we can now solve for our by simplifying this one, we can solve for our volume. So 1.2005 minus 0.1658, we will have 1.0347 volume per meter cube. And cross multiplying, 20,000 will be multiplied to meter cube and is equivalent to 1.0347 volume. Now solving for our volume, dividing both sides by 1.3047. So volume will now become 20,000 meter cube all over 1.0347. So the answer would be 20,000 divided by 1.3047. So the answer would be 19,329.2742 meter cube. And equating this one to the formula of our spherical volume, which is 4/3 pi r cube, and solving for r is equivalent to the cube root of 19,329.2742 times 3 all over 4 pi. Now our radius is the cube 19,000 times 3 divided by 4 times shift pi all over this is to the power of 1/3, and the answer is 16.6485 meters. That's for the radius. And since the problem is asking for the diameter, that means we just need to multiply our radius by 2. Diameter will now become 16.64 times 2. That would be 33.297 meters. And that's the minimum diameter in